Some images have the power to change the world. You might still remember this iconic photo, Earth seen from the moon, taken by the astronauts of Apollo 8. A simple blue marble floating in space, fragile and alone. But today, I want to talk to you about another photo, one that forever changed my view of the world and the universe. And it gave me a strange feeling that haunts me to this day. Get ready, I'm going to show it to you. Here it is. At first glance, it looks like a simple picture of the sky. But I will show you that this photo is far more important than you could imagine. It comes from the James Webb telescope and shows a tiny patch of the sky. At first glance, it seems unremarkable, but to give you an idea, this area is equivalent to the size of a pinhead held at arm's length. But in that tiny space, there are not just a few stars, but thousands of galaxies. Each of those galaxies, like our own, contains billions of stars and probably just as many planets. And that's just the beginning. This photo revealed distant galaxies so faint they were invisible to previous telescopes, including Hubble. Some of them emitted their light over 13 billion years ago when the universe was still young. With just one photo, we have plunged into the past, further than ever before, but there is something even more fascinating. This photo was not taken in any special region of the sky, but in a completely ordinary area, chosen precisely because it seemed empty, yet it is overflowing with galaxies. So imagine, such a small patch is so rich. What about the rest? And the farther we look, the more we seem to discover even more distant galaxies. With each step, the universe reveals new secrets as if there is no end. And then a question began to occur to me, a question that haunted me for days, weeks. How far does it extend? Is the universe infinite? Does it have a limit, a boundary, something beyond which there is nothing? No more stars? No more galaxies at the edge of the universe? Is there a wall or an impassable barrier? But instead of telling you about equations and abstract theories, today I propose something simpler. How about we just go straight? Today I take you on a journey, you and me, inside a hypothetical rocket heading towards infinity. We will discover together what lies hidden at the edge of the universe. First, we feel a slight vibration, then the incredible thrust of the rocket launching into the sky. We have just left the surface of the Earth, our cradle. Just a few kilometers up, the blue atmosphere fades, the sky darkens, and in less than 10 minutes, thanks to its advanced technologies, it reaches a basic orbit, an achievement that seems very impressive at first glance, but in reality it is only the first step. Ahead of us is the International Space Station. It is only about 400 kilometers above the ground, less than the distance from Paris to Lyon. But reaching it is already a feat. A conventional spacecraft takes about 10 hours to reach the ISS after launch. However, this tiny altitude on the cosmic scale is enough to change the landscape. We clearly see the curvature of the Earth, the thin blue layer of the atmosphere, and especially the cosmic silence around us. One might think we have traveled a long distance, but in comparison, the moon is nearly 400,000 kilometers away, meaning 1,000 times farther than the ISS to reach it. Even the most powerful rockets in history, like the Saturn V, took 3 days. A commercial plane takes about a day to fly around the Earth. Multiplying by the stopping points, the moon is 30 times the diameter of the Earth, a journey that defies our intuition. But that is nothing compared to the distances between planets. The Sun, our star, is 150 million kilometers away. Light, the fastest thing, takes over 8 minutes to reach us. A brief 8 minutes for a photon to leave the Sun's surface and hit our retina, but that is an eternity on the scale of our journeys. Humans, not to mention the planets, Mercury, Venus, and Mars, each orbit the Sun at distances of tens, even hundreds of millions of km. Compared to these numbers, the altitude of the ISS, or even the Earth-Moon distance, is minuscule. Now we are far from Earth, far from the Moon's orbit. The further we go, the more we realize that the so-called solar system is actually a vast black desert. The planets and asteroids are just tiny, isolated oases in the silent immensity. First, there is the inner solar system, the region of the 4 rocky planets, Mercury, Venus, Earth, and Mars. In ancient times, people did not know they were rocky worlds. They only saw points of light, these wandering planets we named, and people attributed divine powers to them, especially Mercury. Small, fast, and close to the sun, it rightly bears the name of the swift messenger of the Roman gods, Venus, the goddess of love and beauty, associated with the morning and evening star. Forever closer to the sun, brighter than all other planets, today we know Venus is truly a suffocating hell. Mars, the god of war, appears red to the naked eye. The ancients saw it as a symbol of blood and conflict, but the reality is more subtle. It's its oxidized surface that gives it a deep red color. Actually, it's red because it is rusted in a way. On the scale of our journeys, Mars is already much farther than the Moon, but it is still a neighboring world when leaving the inner planets. Our rocket crosses the asteroid belt, a vast ring of rocky debris. One might think it is a dense field of rocks, but it is quite the opposite even here. The average distance between two large asteroids is measured in millions of km. Our spacecraft speeds along in silence, occasionally encountering a lone rock. Ceres, the largest, is like a drop in an empty ocean. Beyond that, we enter the realm of the gas giants. Jupiter, symbol of the gods, the largest, is more than 5 astronomical units from the Sunday. Each astronomical unit equals 150 million kilometers. Light takes over 40 minutes to travel that distance. For a probe from Earth, that is already many years of journey. The further we go, the more abstract the distances become. Uranus and Neptune, tens of astronomical units away, are just cold blue dots, buffeted by unimaginable winds. The Voyager probe, launched in the 70s, took a decade to reach its edge. Beyond Neptune is the Kuiper Belt, a field of icy objects, where Pluto, once considered a planet, is just one member among many others. New Horizons, one of our fastest probes, took nearly 10 years to get there, and that's not even the end. Further out, at thousands, tens of thousands of astronomical units, lies the Oort cloud, a kind of comet reservoir. It may extend up to nearly 2 light-years, a quarter of the distance to the nearest star. Even with constant acceleration, the concepts of time and distance become vague. The numbers stretch out, becoming immensely large. If the solar system already seemed like a bottomless abyss, what about interstellar space? The universe is a black desert sprinkled with a few bright gems. At this stage, the mind wavers. Where we are, all that beauty is just tiny dots lost in the distance. Our ship hurtles away, and the solar system we thought was vast is only the first step of an endless cosmic staircase. Endless, it's time to go further. We are at the entrance to interstellar space, a void even more vast, where the solar wind weakens, where the direct influence of our star fades, and where the sun's gravity gradually gives way to the gravity of other celestial bodies in the galaxy here. Every direction is the same, no north, no south, and no clear landmarks. The very concept of neighborhood takes on a dizzying scale. The closest star after the sun is Proxima Centauri, about 4.24 light-years away. A light-year is the distance light travels in 1 year. On our scale, that's hard to imagine. Our rockets, continuously accelerating, would need to multiply their speed by tens of times, hundreds, even thousands of times, to make that distance manageable in a reasonable time. And even then, it would still be a colossal journey. Proxima Centauri is a faint red dwarf, not visible to the naked eye from Earth. It orbits near the Alpha Centauri system, a collection of bright stars that, seen from the southern hemisphere, form a familiar landmark in the sky. Proxima has an exoplanet, Proxima b. It lies in the star's habitable zone, meaning the right distance for liquid water to exist on its surface. However, we know almost nothing about this world. Does it have rock, an atmosphere, water? This planet, on a cosmic scale, is right next door to us, and yet it remains a mystery suspended deep in the night. If we continue our journey, we will enter the range of a few dozen light-years around the Sunday. Within this limited bubble, there are about 1,400 solar systems and over 2,000 stars. Including multiple star systems, it's truly a cosmic crowd, but a crowd nearly invisible to the naked eye because the distances are so vast. Among these thousands of stars, most are red dwarfs, faint and cool, glowing with a dim light and lasting for billions of years. There are also larger stars, like yellow dwarfs, similar to the sun, cooler orange dwarfs, and dying red giants, or a few blue stars, rare and extremely bright, heated to such high temperatures that they dazzle their surroundings. And then there are exoplanets from the 90s. We know that exoplanets are not a privilege of the Sunday. Astronomers have discovered thousands of exoplanets. Most nearby systems contain at least a few planets within the habitable zone of their host star. This makes us dream about the existence of liquid. Others are hot giant gas planets, orbiting their star so closely that their year lasts only a few days. Others are super-Earths, larger than Earth but smaller than Neptune, with conditions that can vary from paradise to hell. Look at the Ross 128 star system about 11 light-years away. This modest red dwarf star has a planet orbiting it, Ross 128b, with surface conditions that could be surprisingly similar to Earth. Its mass is slightly larger than Earth's, and its gravity is only slightly stronger. The temperature could be just a few degrees lower than Earth's average temperature. This is a potentially temperate world, possibly a paradise, but it is so far away that even at the speed of light, it would take us more than a decade to get there. At a distance of 16.8 light-years, we encounter Altair, a bright blue-white star, larger and hotter than our Sunday Aberdeo. Altair rotates so fast that it is flattened at the poles. Further away, at 25 light-years, we approach Fomalhaut, a triple star system with a young yellow primary star. It is surrounded by a protoplanetary disk, gas and dust, a true cradle for future worlds, yet stars do not last forever. They are born, grow, consume nuclear fuel, and sometimes give birth to planets. And eventually they die, leaving behind white dwarfs, neutron stars, or sometimes black holes. We could spend hours, days, years telling about each neighboring star, each unique feature, each strange exoplanet. Some worlds might be vast oceans with no solid surface. Others are ice deserts or volcanic furnaces. At such distances, our knowledge remains fragmentary. Based on some measurements of stellar radiation, gravitational oscillations of stars, and the filtering of a planet's faint light as it passes in front of its star. As we move away from the nearest stars, we enter another dimension of vastness, the galaxy, the Milky Way, our cosmic home. We have just left a bubble about 50 light-years in diameter, filled with thousands of stars, but that is just a drop in the ocean. The Milky Way is about 100,000 light-years across, a spiral disk with a few hundred billion stars. The Sun, on our scale, is just an arbitrary point about 25 light-years from the galactic center, nestled in a minor spiral arm, called the Eastern Arm. Most of the stars we see at night or detect through telescopes, they lie within a radius of a few hundred, even a few thousand light-years. A tiny volume compared to the total size of the galaxy. Let's try to imagine the scale. If the Sun were shrunk to the size of a blood cell, then the Milky Way would be as large as a continent, a Europe 3,000 kilometers wide. The space between stars is immensely vast, and what we once considered huge interstellar chasms are actually just small gaps. Here we are talking about traversing not just a few light-years, but several thousand. Then it is tens of thousands of light-years just to cross an arm of the galaxy. We have to imagine enormous time spans at extremely high speeds. At the center of the galaxy lies a fascinating object, a supermassive black hole named Sagittarius A. Its mass is estimated to be about 4 million times that of the Sunday. Around it is a huge bulge of old stars tightly packed in a region with much higher stellar density. From there, spiral arms rich in gas and dust, along with star-forming regions, emanate. And in star-forming regions, nebulae are examples of stellar nurseries, bubbles of gas and dust that give birth to new generations of stars and planets. Now, our ship continues to accelerate, but even if we could travel at a significant fraction of the speed of light, crossing the galaxy remains a colossal task. At elevator speed, Voyager 1 flies about 14 kilometers per second. It would take 550 million years to reach our point when leaving the Milky Way. Our spacecraft enters a territory where distances are measured not only in thousands of light-years, but also in millions. The local group, comprising about 50 galaxies, is dominated by 3 spirals. The Milky Way, Andromeda Galaxy, and Triangulum Galaxy span about 10 million light-years. Around these giants orbit dwarf and irregular galaxies, sometimes only slightly larger than a star cluster. The Milky Way, though gigantic, is just one island among others in a galactic archipelago. Andromeda is located about 2.5 million light-years away. It is the nearest spiral galaxy and is believed to contain 5 times as many stars as the Milky Way. It also has a complex nucleus, suggesting that it has devoured other galaxies in the past. Our spacecraft, still accelerating, traverses this intergalactic space. The galaxies in the local group do not simply sit still, they interact gravitationally. The future collision between the Milky Way and Andromeda in about 5 billion years will be an event of unimaginable scale. 2 giant spiral galaxies merge to form a larger elliptical galaxy, but for us, those billions of years are almost abstract. We fly through in a few moments regions that even light takes millions of years to cross. If we zoom out our view even further, the local group appears as a small entity in a much larger structure, the local sheet, than the Virgo supercluster. These galaxies are not simply scattered randomly on large scales. They gather into filaments, clusters, and superclusters, forming a cosmic structure that evokes a giant spiderweb. The Virgo supercluster that we belong to spans over 150 million light-years. It contains thousands of galaxies distributed in clusters and groups. At our speed, relativistic effects begin to be felt. Past, present, and future become almost abstract concepts, distorted by our speed of travel. Space itself contracts in the direction of our motion, making what is theoretically unreachable much less distant. But this relativity is not enough to erase the enormity of distances, and that is not all. At these scales, the expansion of the universe begins to appear. Beyond a few 100 million light-years, galaxies move apart like dots drawn on an inflating balloon. That is an effect of cosmic expansion. The farther we look, the faster distances increase. This expansion, whose existence we have only skimmed, will become crucial to understanding the ultimate limits of our journey. But for now, just remember that at the supercluster scale, gravity is not enough to hold galaxies together. Entire parts of the universe are moving apart, and some objects, though bright, may never be reachable because their light may never reach us. Thus, on the scale of the local group and superclusters, we realize that our galaxy is just one brick in the galactic wall. It is itself infinitesimal compared to the entire universe. Even with our rocket, with unlimited acceleration, we are only plunging deeper into a bottomless abyss. Stepping back, we see that the universe is like a giant fractal maze, where each level of structure contains a larger one. We have reached the ultimate limits of cosmic expansion, where even light is insufficient to illuminate the distant abysses. So far, we have passed through the solar system, the stellar neighborhood, the galaxy, and the local group. Then, we traveled through superclusters of galaxies, realizing at each step that the universe is far more vast than anything we had ever imagined. Yet, even after traversing hundreds of millions, we continued. Then, after billions of light-years, we found no boundary, no solid wall, no sign saying end of the universe. We are facing a more subtle horizon, the cosmological horizon. That cosmological horizon is precisely that boundary. Beyond that boundary, light has not had enough time, since the Big Bang, to reach us. To understand this, we need to recall that the universe has a finite age, about 13.8 billion years. Light travels at a constant speed, so there exists a region from which no photons can reach us. This wall is not a material barrier, but an effect of time and the finite speed of light. From Earth, the observable universe forms a sphere with a diameter of 93 billion light-years, much larger than 13 billion light-years. Because the universe has been expanding since the light began traveling. Therefore, regions that were once closer have become distant. But there is an even more extreme concept, the Hubble wall, or Hubble sphere. That is the distance at which the expansion of the universe causes objects to recede faster than the speed of light. Not because those objects are moving faster than light locally, but because space itself is expanding. Therefore, beyond a certain distance, light emitted today will never reach us. Because space stretches faster than a light ray progresses, we touch upon the true dynamic nature of the universe. The expanding nature of the universe and the existence of the cosmological horizon cannot be conquered. Some regions of the universe remain and will forever be beyond our reach. And this is where questions from theoretical physics about the shape, size, and geometry of the universe begin to play a role. What shape does the universe have on the other side? Is the universe flat, open, or closed? The answer depends on the total amount of matter and energy it contains, as well as its critical density. Critical density is a theoretical equilibrium point that determines the curvature of space itself. If the total density of matter and energy exactly matches this level, the universe expands in a geometry called flat. In such a universe, the familiar rules of Euclidean geometry apply. Parallel lines never meet, and the sum of the angles of a triangle remains exactly 180 degrees. And space then can expand infinitely without ever closing. If the density exceeds the critical value, everything goes in a different direction. Space then has positive curvature, like the surface of a sphere. But here, it is a four-dimensional structure curved in such a way. In a universe called closed, we could go in a straight line many times and eventually return to the starting point. This is somewhat like traveling around the Earth with an extra dimension. The universe would have no literal boundary, but would be finite, contained within itself. Conversely, if the density of the universe is lower than that famous critical density, the curvature becomes negative, reminiscent of the shape of a saddle. Here, trajectories behave strangely. Parallel lines will increasingly diverge, and the universe will expand infinitely. It may also be infinite, but very different from a flat space. This open geometry suggests a universe where concepts of distance and direction become increasingly blurred, transforming our understanding of what is straight or curved. Actual cosmological data, especially obtained from the cosmic microwave background, shows that the universe is extremely close to flat, with a very small margin of error. That means within our observational limits, the universe appears nearly perfectly flat. If it is completely flat, it could truly be infinite. If it is nearly flat, it could still be immensely large, with a radius hundreds, even thousands of times larger than the observable universe. In other words, even the most optimistic scenario shows that the universe extends far beyond everything we can see. What we call the observable universe is merely a tiny fragment of a much larger whole. This conclusion has overwhelming implications. Even our magical rocket capable of constant acceleration could never explore the entire universe. At best, we can explore an increasingly larger portion of the observable universe, but the rest, beyond the cosmic horizon, will remain forever hidden. And if the universe is truly infinite, no journey, no technology could allow us to explore all of it. Even the minimum size of the universe, determined by cosmological measurements, ensures that it is already too large for us ever to hope to circumnavigate it. Science can only give us an estimate, not an absolute certainty. It gives us limits, constraints, beyond the laws of physics, the speed of light, and the expansion of space. Those determine that we cannot observe any further, and perhaps we will never know anything about what lies beyond. So unfortunately, there is no easy answer. We do not know whether the universe is infinite, nor do we know where its boundaries are, if they truly exist. And yet, it is this very uncertainty that moves me. Even with a ship of infinite energy, accelerating forever and with unlimited time, we could only explore a tiny fraction of the universe. We will never reach an edge, a final wall, an endpoint to our adventure. And it is that feeling that this image, which stirred everything within me, makes me feel. It reveals a host of galaxies invisible to the naked eye. That reminds me of the vastness of our universe. That vastness surpasses reason, surpasses numbers, surpasses everything our minds can conceive. And at the center of that infinite ocean, our Earth appears only as a tiny oasis. It is a small island of complexity and life in a dark and silent desert.